So expectation, what does it mean? In English, you expect something. What's your expectation on something? You can probably gauge what it means in this case. But we are looking at the word expectation here in the context of random variables, which is the new friend that we got introduced to last week, in which instead of describing every single possible outcome that could happen from our experiment, so here is our S, aka all of the possible outcomes of our experiment. Instead of describing them one by one, for example, the tuples of 2 dice, imagine if we had 5 dice, then the 5 tuples of the 5 dice. Instead of doing that, we instead map each outcome to a certain value, a certain number that is a real number. So this way, we don't have to worry. We don't have to go over the details in that meticulously, but we can abstract it and we can talk about just the overall, the higher level outcomes. We already looked at 2 different types of random variables, the discrete ones and the continuous ones, which, as their name suggests, talk about discrete values and continuous values. And we also know that we have these 3 friends. It's no longer typo, right? No, it's not typo anymore, which talk about the distribution of the probabilities of those random variables. We have the probability mass function. We have the probability mass function, the cumulative distribution function, and the probability density function, which will talk about the probability of your random variable being in different, having different values. So PMF is exactly having the probability of that point. And here is the probability up until that point. And for the probability density function, it is the probability between 2 points or an interval. So remembering those 3 things and how we can describe the probability of our types of variables, we now go on to expectation. So as the name says, what do you expect it to be? In this case, the random variable. What do you expect it to what value do you expect it to have? Like, for example, if I ask you, oh, I have an experiment, I have a die, and I'm going to, I have 2 die, and I'm going to roll my 2 die, and I'm talking about X is the sum of the 2 dice, and I ask you, what value do you expect would come? Like, what's the default do you have in your mind? Would it be 6? So you would have maybe 3 and 3, 4 and 2, and so forth. Would you assume that the average would be 1? Sorry, that's not possible. Sorry, 2, which is 1 and 1. What do you think it would? What would you expect the value to be? And that is the representative number that you usually go to in your head when you talk about that random variable X. So you can look at it as the center of gravity in the sense when you have, when you have the PMF like this, you have 3 possible values, 2, 3, 4, and you know that the probability of each value is 0.1, 0.7, and 0.2. And if you were to balance this seesaw, you would probably like to put your center of gravity there, just so that your seesaw doesn't tip over. So we can see here that more or less the expectation of this particular X is somewhere around 3 point something, and this is your center of gravity. If you want to compute it mathematically, you can compute it if you have a discrete random variable as such, and if you have a continuous random variable as such. It makes sense, right? So let's look at it. It is the sum here of the value times its probability. So note here we have a PMF, and here we have the probability, large p, small p, don't forget. So it makes a lot of sense. So it's the value times the probability of that particular value times another value and the probability of that particular value, and so forth. You sum it up, that is your expectation. That is for a discrete random variable, but your continuous random variable follows the same logic, only that instead of summing it up, you use the integral. between negative infinity and infinity, and you substitute x1 xi, like any x, with your function instead of your PMF. Often this is referred to as the mean, or also the average or the mean of the random variable. So for example, when we talk about the outcome of rolling a fair die, we can define our x as this rolling outcome, or outcome of fair die. And we can also now define the probability of x being 1 is, it's one die, right? So 1/6, which is the same as any x, 1 until 6. It is 1/6, where xi is 1 until 6. Because we assume that each side of the die has equal probability. So if I use the equation of ex, or expectation of x, then I need to, let's go here, I need to sum up the probabilities from 1 to 6, xi, and the probability of x equaling xi, alias 1 times 1/6 times 2 times 1/6, and so forth, 6 times 1/6. And let's see, yes, I'm correct. And I haven't done the computation until the end, but you get the general idea. The second example is a continuous random variable. So we have a the PDF, and we want to compute the average time to wait for the train. So here we have as was this equation here, we need to compute the integral from negative infinity to infinity, x times the function dx, because we're integrating, sorry. And since our function here is only valid from x larger than 0, then we can put the lower limit as 0, but our upper limit is still infinity because it doesn't have an upper limit in this range here. And obviously you have calculus here. Don't forget that this is probably solved using partial integral. So this is u and this is du and so forth. But take my word for it, it equals 1. And that means that on average, you need to wait for 1 hour if we're assuming this type of PDF, or probability density functions. So since we already have these values, there are some properties that they must fulfill, and we know, and we can use them in order to manipulate the expectation values. Like in this case, we have, you guys have taken linear algebra, right? So we know that the linear combination of this expected value of a certain random variable can also be extracted as such. We also know that constants can be taken out. So A can go out here. And we also know that an expected value of a certain number will equal that number itself. So recall the notation for expectation. So it's usually using a square bracket like that. And note that you can also compute the moments of the expectation of the random variable. So when I say ex, it's the same as writing ex to the power of 1, right? So that's the first moment. And the first moment is the mean. And then the second moment, the third moment, and so forth can also be computed as an extension of the original equation of expectation as follows. So note that previously when we were computing ex only in a discrete case, we have the sum of x1 and times the probability of x equaling x1, alias the sum of x1 small p x1. But here you notice that when I'm talking about the nth moment, this x here, I need to put it to the power of n. And thus we have this, not modification, we have this derivation of the original expectation equation. Okay, so now when we already know how to compute it, now what information does it give us? What use can we take of it? What can we make of it? So I already went over this briefly last week. So since it gives you the mean, we already learned this in descriptive statistics, more or less it gives you the measure of central tendency. In other words, when I say the expectation of this variable is 2, I know that most of the possible values will center around 2. It's not going to be around that. That's more or less where everything is, where all of the possible values of x are gathered together. However, I have no idea yet about how far these values can go. I only know that it'll be centered around 2. I don't know how far left it will go, like how small the number could be and how far right it would go, or how large the number can be. Like in this case, in this example here, I have 3 random variables, z, y, and w. I know that here the expectation are identical for all of these 3 random variables. However, you can see that the ranges or the variance of these values are very different. The first one, w equals 0, it's just there in 0. Y goes to 1 and what minus 1, and z goes to 100 and minus 100. So just like when we were studying descriptive statistics, we need some additional statistics. We need some additional measures to be able for us to be able to describe our random variables. So instead, in addition to the mean, we also have the variance, just like what we had in descriptive statistics. In the case of a random variable, you can compute variance based on the expectation itself, which is, this is the equation that you need to remember here. So the expectation of x squared. So here, what is being squared is the x alias. This is the second moment. Remember, we talked about moments. The second moment of x, and this one is our basic expectation. So our first moment, alias expectation, then we square it. So here is our second moment, and this one is our expectation squared. And thus we can compute the possible or the range or the variation of the values of x. Sorry, give me a sec. Let's do that. And obviously, when we're talking about variance, we also have to consider standard deviation. And as we already came to know in descriptive statistics, standard deviation is the square root of variance. So in our previous example, when we were computing the role of the fair die, so we computed this one. So we know that px equals xi equals 1, 6 for xi equaling 1, 2 until 6. And our expectation when we were computing it, it was something like 1 over 1/6 times 2 over 2, 1/6 and so forth. And the sum is 7 over 2. So we knew that Ex was 7 over 2, and now we want to compute the variance. So recall, there's 2 things that we need to compute. First, we need to compute the second moment, and then we need to square the expectation itself. So let's compute the moment first. So recall that when we're computing the moment, we also need to sum x, something like that. In other words, 1 to a power of 2 times the probability plus 2 to the power of 2 times the probability up until 6 to the power of 2. Oops, not plus. Times the probability. And I already have the answer here. It's something around 91/6. Please fact check me in case I have miscalculated. And thus, when I'm computing variance, I have here 91/6 minus, we already know that the expectation is 7/2, 7/2 squared. I think that is correct. Yes. So here we have 91/6 minus 7/2 squared, and the final answer of the variance is 35/12, which is something like 3 point something. No, almost 3. So 2.9 or something. And just like the expectation, which is the mean, the variance also has some properties or some identities, more or less the same, where we have the linear combination of x in this form. We can then compute for any constant a and b, and we have these identities as well. So up until now, we have talked about the measures of central tendencies as well as the measure of variance in this case. But remember when we were studying the basic descriptive statistics, we also sometimes want to know the relationship between variables. So variance is describing one variable. Mean or expectation is also describing one variable. But what if I would like to know the relationship between x and y, x and z, and so forth? We have what we call covariance of two random variables, x and y, written using the notation cov or covariance, which can be computed as follows here. And we can compute it to get some ideas about these two random variables. So remember that just like when we were talking about correlation, more or less, covariance also tries to map the linearness or the linear relationshipness between two variables. So if it's 0, it means it's non-correlated. It has nothing to do with each other. If it's 1, that means it's very strongly correlated, and so forth. But be careful and don't mix up between uncorrelated and independent. Remember, we have two different terminologies here. We have uncorrelated and we also have independent. However, they are not totally irrelevant of each other, because if they are independent, then we know that x and y are uncorrelated. However, it does not work the other way around. So if you can prove independence, then you can prove uncorrelation. But if you can prove not correlation or uncorrelation, then you cannot prove dependency or independency. So these are some identities of the covariance. These are some rules that you can use to derive or simplify covariance equations. But recall when we're talking about independence here, so how can I prove that it's independent then? Remember, in our previous materials, we already had some different ways of computing independence between variables. We could use the probabilities, right? We could also use the PDFs and CDFs as well. Additionally, you can also prove that two RVs or two random variables are independent using their expectations as well. So I think by now we probably have around 3 ways in which we can use to prove independence between two variables. In this case, we're talking about independent RVs, so we can use the expectation as well. So it only happens, you can say that x and y are independent if their expectations also fall into this category, or you can prove it by using this equation. Okay.